So, like I said that although on paper when you look at it, it would seem like tetrahedral void in BCC would be preferred by carbon atoms, but it is not really the case. Octahedral voids are the ones where carbon atom sits. Now, at this point let us also look at what will be the radius of these voids. So, I have shown you the ratio, now let us look at the actual value. Radius of void, so this comes out to 0.291 angstrom, this comes out to 0.534 angstroms. For this one it comes out to 0.364 angstroms, and for here it comes out to okay. And at this point let me also give you what is the radius of FCCFE. Yeah, it is a little different. So, the radius of FCCFE is a little different from radius of BCCFE. But not by much, thankfully for us. And what is the size of the carbon atom that has to sit over there? So, the carbon atom is equal to 0.77 angstroms. So, the first thing that you have to realize, let us first look at this, even this simple one where everything is going as per we expect as per our expectation. So, the carbon is sitting at the octahedral void and here the octahedral void radius is 0.534 angstrom, while the real size of the carbon atom, radius of the carbon atom is 0.77 angstroms. So, a larger atom is fitting in a smaller size, just what I told you earlier, that the presence of interstitials causes a lot of strain in the matrix around it. So, such a large 0.77, meaning it is more than 20% larger in size than the available void over here, and still it goes into that side, it has to go in that side, it prefers for the reason of thermodynamics, because it leads to lower free energy. The presence of these atoms in that place leads to lower free energy, and therefore, the carbon atoms goes there, and all the strain energy that is caused is included in that enthalpy of formation, because some amount of energy will have to be put into the system to accommodate that strain. And in spite of all that, because of the configurational entropy, we are able to achieve, or the system is able to get lower energy by addition of this carbon atom. So, this is something that would appear quite counterintuitive on the first encounter. Now, let us look at the second aspect. We are saying that here the radius of the octahedral void is 0.195, which is like maybe approximately 1/4 of the radius, actual radius of the carbon atom, and still the carbon atom is sitting over here instead of a much larger size, which is 0.364. And what is the reason for this? The reason for this is hence. Now, we looked at the fact that the tetrahedral void and octahedral void are distorted. So, how are they distorted? Because we saw that all the lengths are not equal. Now, let us look at it in a little bit more clarity. So, first let us look at the octahedral void. So, the octahedral void, if you look at it, is something like this. What I am trying to show here is that these two atoms are much closer. So, these two atoms are much closer. The atoms on the plane, they are far apart, and the size of the void is limited primarily because of these two atoms. The size gets limited because of these atoms. Now, what is the easiest way to increase the size? Push these atoms apart. So, just by pushing two atoms this void can be increased in size from 0.195 to 0.796 angstrom. So, you will have to cause a little bit of strain. So, that will get included in the enthalpy formation and by pushing those two atoms, these atoms whatever is the interstitial over here, which is carbon in this case, the carbon can increase the size from 0.95 angstroms to 0.796 angstrom, which is a big deal. Now, if we look at over here in the tetrahedral void, this is also distorted. However, in this particular case, if this atom has to increase the space, it will have to push apart all the 4 atoms. So, has to push apart all 4 atoms to fit in void. So, you remember this, even this 0.3, so its original side is 0.364 angstroms. So, even 0.364 angstrom is very small, it is almost half of what is less than half of what is actually needed. So, this is still very small and the atoms have to push the atoms of the corner atoms apart, and here it has to push 4 atoms apart. Here it has to just push the 2 atoms apart and it will be able to accommodate or increase the void size from 0.195 to 0.796 angstroms, and therefore, this can easily fit inside this. So, this is the primary reason why carbon prefers octahedral site in BCC. Okay. Now, let us come back to which one. So, we have understood one aspect, which is when we said that octahedral voids would be preferred. So, now we understand why. Now, the second aspect we need to understand is which one will the carbon atom sit more preferentially. So, here let me give you some information about what is the real solubility. So, the solubility of carbon in BCC is 0.008 weight percent at room temperature, and if you go to much higher temperature, which is it reaches 0.025 weight percent at 723 Celsius. On the other hand, solubility of FCC can be as high as 2.1 weight percent, although it is at a little higher temperature, which is 1147 degrees Celsius. So, now what is the reason that even though BCC is the more open structure, but still the carbon atoms are more soluble in the FCC, and the reason for this is when you look at the number of voids per unit cell or the number of void per unit atom. So, what do you see here? The total number of void is only 3 per associated with each atom. Here the number of void associated with each atom is 9. So, although the structure is more open in BCC, but the size of each, because of the large number of voids, the size of each void is very small, and hence, so we can write it like this. So, this is one of our one understanding. Second understanding is that number of voids in BCC is much larger, hence size of each void is very small, hence not very good solubility. So, this helps us understand the interstitial impurity point defects. So, you can see that there are so much intricacy involved in understanding a simple point defect, which is but in this particular case the interstitials. So, you have a more open structure like BCC and still the carbon is more soluble in FCC. You have a larger tetrahedral void, but carbon atom prefers to sit in the octahedral void. Why? Because here just by in octahedral, by distorting just 2 atoms it can increase the size. On the other hand, in tetrahedral void it will have to push away or distort 4 more atoms to be able to accommodate, and therefore, the total space available in octahedral void is larger. So, in both FCC and BCC it so happens that carbon sits in the octahedral void. Okay, so, with that we complete our understanding for this impurity defects, which is the interstitial as well as substitutional. So, we have looked at the vacancy defects, we have looked at interstitial and substitutional defects. Now, what we need to do is look at this whole understanding again from the point of view of a defect reaction. Okay. So, you would see that these defect formation can also be written like a reaction, and hence if it is a reaction you can find rate constant, equilibrium constant, and from that equilibrium constant again you can find what will be the equilibrium concentration, and you would see that it is a much more direct way of obtaining equilibrium concentration. So, our next topic is defect reaction. What is a defect reaction? How would you define defect reaction? Generation and annihilation. Of point defects can be treated as a reaction. Equilibrium concentration can be obtained using thermodynamics. So, now that it is a reaction, so equilibrium concentration can be obtained thermodynamics of chemical reaction. So, now when we treat it as a defect as a reaction, then there are certain rules. What are those rules that we have to follow, that we must ensure that they are taken care of before we can call it a reaction? So, first one is that a solid containing defect should be treated same as a solid solution. So, whether you have A plus B 2 different atoms or you have A plus some defect, both of them are like a solid solution. So, solid containing defect is equal to solid solution. So, it has to be treated like a solid solution, and that we have already seen even when we were trying to get the configurational entropy, that it has to be treated like a solution. So, that is one thing. Mass balance, when you write it as a reaction, then on the left hand side and right hand side you should have same masses. Of course, here vacancies, and if you are talking about charges, then holes, vacancies and holes have no masses. So, you need not worry about the mass balancing of these entities. Electroneutrality. One of the primary purpose of treating these as defect is that we can understand how the charges are being distributed, and therefore, it is much more useful for electronics and ionic solids. So, net charge should before and after reactions should remain constant. Now, this is also something very difficult to achieve or difficult to write as an equation. So, first to maintain electroneutrality or to write a equation where the charges remain same, it is a little difficult, and therefore, you have to adopt certain, you can say, protocol or naming system nomenclature. So, it can be either effective charge, where you show what should be the effective charge on a particular site. So, you go by that effective charge, maintaining that effective charge before and after, or you can go by actual total charge. So, that actual charge, but whichever you choose, you must maintain the same set of system. You cannot mix between effective charge system and actual charge system and expect to get electron neutrality on left hand side and right hand side. So, you have to in most of these, particularly what we call as Kroger-Wink, effective charge is used, and it is found to be much more easier to understand and write down a equation. Now, like I said, we are talking about ionic solids. So, the ratio of lattice sides, for example, if you are talking about MO, so there is one M, one O. So, the total number of sites for M and the total number of sites of O should remain equal, and similarly, if there is some other system M2O3, then the site for M and O should remain in the ratio 2:3. So, that is what I mean when I say ratio of lattice sides should be maintained. So, if it is 2:3, then it must remain 2:3, otherwise it will also violate the total principle of electron neutrality for the whole system. However, we are only saying ratio of lattice sites. The total number of lattice sites need not be kept constant. Meaning that if you add, if you are talking about MO type of system, if you add a site for M atom, there is one site that has been added, then you should also add one site for O atom. So, the ratio would still remain constant. So, the ratio is constant, although the number of sites for M and the total number of sites in the system is not constant. Now, that we are looking at this, like I said, we have to adopt a certain procedure or certain protocol, and one of the protocol or nomenclature that is very effective to use is Kroger-Wink. We will understand this notation system using NaCl. So, NaCl is our system where Na can be considered, where the place where Na sits we will call it at A site, where the chlorine atom sits we can call it B site, and let us assume that as impurity we have Ca, calcium plus plus. So, this is a system that we will use in order to explain this Kroger-Wink notation. And here, as I said, that calcium has 2 plus plus charge, and NaCl, as we know already that Na has 1 positive charge and chlorine has 1 negative charge. So, now let us look at, now there are 3 different kind of sites: A site, B site and interstitial site. A atom, which is Na plus, B atom which is Cl minus, and when we are talking about atoms, then there is absence of atom which is vacancy, and then there is C atom which is Ca double plus. Now, when A atom, which is Na, sits at its own place, then we denote it by Na subscript Na, and when Na is sitting at its own place, we use in this particular system the case of effective charge. So, although Na has a plus 1 charge, it should be Na plus, but Na is at its own side. So, so how different is it from 1 plus 1 charge that it should be there? It is 0. So, it will be called neutral in that sense, and hence it is represented just like that, or Na subscript Na and a cross. Cross means there is no charge over there. Now, let us put a Cl atom at Na site. Now, where there should have been +1 charge, but now chlorine minus atom is sitting over there with its minus charge, which means it is 2 less than what it should be, and therefore, it will be represented as 2 minus, and the way to represent 2 minus is like this. So, they have 2 dash, meaning it has 2 less positive charges than what it should be. Keep in mind, we are in this particular system we use effective charge. Let us go to vacancy. So, let us say a vacancy is sitting at a sodium site, and it vacancy in general will not have any charge on it, and therefore, it is 0 charge, but it is sitting at the sodium site and there should have been a +1 charge. So, it is 1 less than what it should be, and therefore, it is 1 negative charge. Now, let us say that calcium atom is sitting at the sodium site. Now, calcium, like I said, has plus that is 2 plus charges. So, it is 1 more plus than what that particular site is supposed to have, and therefore, it will be represented as 1 plus, and the 1 plus is given by dot. So, this dot means plus, dash means minus. So, this is how the different atoms sitting at Na site would have effective charge. Remember again, these are the effective charge. Now, let us come back to B site. Now, let us say B site is for the chlorine. So, let us say we have sodium sitting at chlorine. Chlorine should have -1, but sodium is actually sitting with +1 charge. So, it is 2 more positive than what it should be, therefore, it is Na plus plus. If Cl is sitting on its own site, then there is no effective charge. Therefore, you either show it like this, or like here you will put a cross. So, we will be interchangeably using this. So, do not get confused, we can both of these represent that there are no charge on this. Plus and minus are very different. So, it will not get, you should not get confused with that. Now, vacancy sitting at chlorine site, it should be -1, but it is 0. So, it is 1 more than 1 positive compared to chlorine. So, it will look like this. Calcium is +2 when chlorine should have been -1, which means it is 3 more positive than what it should be. So, it becomes 3 positive like this. Now, let us come to the interstitial site, because we are talking about impurity. So, impurity like we saw can be substitutional as well as interstitial. So, let us say that sodium atom is sitting at interstitial. Interstitial is not supposed to have any charge. So, this is 1 positive, because Na is with 1 positive charge. So, whatever that charge is more than what is expected. So, it is shown as 1 dot. Chlorine sitting at this place is 1 minus charge. This chlorine has 1 minus charge, but it is not expected to have any charge. Interstitial is not supposed to have any charge. Vacancy. Now, all these sites are actually vacant. So, this is just a simple notation just to keep track of interstitials. Otherwise, it means nothing, and therefore, there should be no effective charge on this. Calcium sitting in the interstitial, again it has 2 positive charge, and it is not this interstitial site is not supposed to have any charge. Therefore, this is Ca double dot. Now, if you understand this, then try to guess what will be the meaning of V chlorine cross. Now, you have seen V chlorine plus, which means that vacancy, there is 1 positive effective charge. Now, let us say that I have put it as a cross, meaning vacancy with chlorine, vacancy sitting at chlorine site with no effective charge. It would mean that this site has 1 electron localized. Now, if chlorine were there, then chlorine would have already had 1 negative charge, meaning 1 electron over there. Now, if there is no chlorine, but still there is 1 electron over there, that is why the effective charge is still nil, meaning it still has as much charge as it was expected to have. Similarly, if VNA is shown as like this. Sodium was supposed to have positive charge, and vacancy in that place is if it were vacancy without any charge, then it would have been 1 negative like we have shown over here. But here I am asking you this notation where it is shown as effective charge as 0, nil. It would mean that vacancy is having one deficient electron, meaning something like a hole. So, site has one hole localized. So, with this we can move on to look at some of the simple equations that we had written earlier. So, if we go back and say how a Schottky defect should look like in something like a M plus 2 O minus 2. So, it is a MO system where it has M with plus 2 charge and O with minus side. So, M sitting at M with no effective charge, O sitting at O with no effective charge, and since this is a reaction which can go in either way. Now, let us say this is a Schottky defect. So, there is a vacancy at the cation site and that and a vacancy at the anion site. So, vacancy at the cation site. Now, there is no atom at this particular metal site and it has no charge associated with it, which means no real charge associated, which means effective charge is minus 2 minus. Then there is VO, there is oxygen site where there is nothing, no atom present there with no charge, no real charge, which means effective charge is 2 positive. And then there is still other atoms with MM plus OO, which means that we can also write it as 0, meaning perfect crystal, this is not trying to maintain the total number of sites. Okay, we are not trying to show the total number of sites. So, the total number of sites, like I said, need not be maintained, only their ratio. So, now this is that is why here the total number of sites has not been maintained, but this vacancy ratio has remained same, and therefore, we can write it as Vm. So, this is how you can write as a defect reaction a Schottky defect. So, we will look at more examples on this in the next class, and in the meantime you can try how you will write say a Frankel defect. So, see you in the next class.